Good morning, everyone. Yeah, I uploaded the wrong lecture the last time. I'll be correcting that. I got a mail, and thank you so much for pointing it out. Okay, so continue at chapter 15, the second discussion section of the chapter. So today we'll be looking at graphical and mathematical representation of wave and other subtopics as well will be discussed. The last class, we discussed the wave model and we saw some terminologies we used to describe the wave. We were able to talk about the transverse and longitudinal wave, the two major class of waves. And also we looked at mechanical and electromagnetic waves, in addition to matter waves, okay? And we didn't really go deep into matter wave, but we just mentioned it as part of the types of waves to be considered. Okay, so today we look at graphical and mathematical presentation of waves. And we want to emphasize that a wave is not localized at a single point. It exists and is changing with time throughout the entire medium. As it travels, it's going to be changing. It's not localized to just one point like we see in objects, okay? Also, we want to point out that because they are not localized at a single point and they change as they travel through the medium, this makes the description of wave something dynamic, and their motion takes a bit more thought to describe than just the motion of particle that we can easily say it's moving from A to B and we'll draw the trajectory. Because wave most times is occupying the whole medium, it's not just one single trajectory that we can draw. So we have graphical and mathematical ways to describe that as well. Okay, so we'll be looking at that in details in the next few slides. So to describe wave mathematically, we need to use functions of both time and space. And we'll be representing that with y, x, t. Y as a function of s and t, that is function of position, which is x, and then function of time. Okay, so we'll be saying y, x. When we say that, we mean y, or displacement with respect to position. And when we see yt, we are referring to displacement with respect to time. So we'll be using this to describe the wave mathematically, saying it's a description of the function of both space and time. But before we go into the description of the mathematical representation of waves, we want to quickly look at two major graphs that we use to present waves as they travel through a medium. Okay, so the two kind of graphs we use to describe wave, they are called the snapshots and the history graph. Okay, so let's see what the difference is between the snapshot and the history graph. Okay, as the name implies, snapshots. We use snapshots to describe the instant state of a wave. So a graph that shows the wave displacement as a function of position at a single instant is called the snapshot graph. So we use it to describe that instant state of the wave motion. So the snapshot graph shows us the motion of the wave at that instance. Okay, so the figure here is just a typical snapshot graph of the wave traveling in this direction. So the string displacement as a function of position is emphasized. Okay, so we see x here as a function of position. And then if you look at this side, the image shows the sequence snapshot of wave, the same wave as it's traveling. We took a snapshot at different times. You see the first snapshot, and then it moved a distance of change in s. We take the second snapshot. We see that the wave is moving without changing its shape. The shape keeps moving, okay? So the shape is not changing, but the position is changing. So this is a snapshot with respect to position. And the position from the definition of velocity as displacement over time, making displacement or position subject of formula, we have V equal to a change in X, change in position being equal to V times change in T, which is time, velocity times time. Okay, so we already know what this means from our definition of velocity. So let's see the history graph. I said we use these two graphs. Remember, we're looking at graphical and mathematical presentation or description of wave. We use these two graphs to describe wave. The first one, which is a snapshot, describes the wave at that instant. And by the time you take several snapshots, you'll be able to get like a trajectory or a trace of that wave motion. Okay, so that's why we said snapshot can give us the wave motion. Now, the history graph is a record of the motion of one point in the medium over time. So like the name implies, history is going to give you like the history of the journey of that medium or the journey of wave through that medium. So let's see quickly how the history graph is constructed. So we have the first part, several snapshots, the snapshot graph. Now we combine this snapshot graph to construct the history graph. Okay. Now, if you look at the snapshot graph, you see, let's assume we have a dot on the part of that wave. As the wave is coming, it gets to this dot, you see the dot quickly rise, and as the wave is passing, the dot starts descending to it gets to the level flat. So we took the snapshot as it's coming close after the dot rise above the peak and descend and go to the bottom. And this is how we constructed it into historical wave. This here is giving you it's a negative graph. Now notice that the shape of the wave traveling here has its peak pointing towards the right, but our constructed graphical historic graph is opposite in direction. Most times when we do construction of history graph, it flips the shape, but not in all cases. Okay, so we take the typical example of a case where it flipped. So we'll have like a flip or a reverse of the trend here represented here. So here is a negative graph, a negative slope. The point is on a negative slope and the flip is positioned on the positive. And we see also these are positive slopes here, positive, positive, and then the flip gives us negative. So at this position, this is it. At this position, this. and at this position this. So the graphing of the motion of the 1 point on that part of the medium gave us the history of that graph at different time t. You notice that the earliest, the earliest point t1, and then progressively as the wave passes through that dot, we see the t2, this time t2, time t3, and time t4. Okay, so this is typically how the history graph is constructed. It gives you the history or the journey of the wave motion. All right. So I said that we noticed that there was a flip here, and we emphasize that it does not really happen in all cases, but most of the times there's always a flip. So let's look at this class activity. The figure here to the right is a snapshot graph of a wave moving to the left. This is the direction of the wave. Following the approach of the history graph we just saw, which graph below is the correct history graph for the point, this point, in the snapshot graph marked with the dot? Okay. So, we mentioned that the history graph we saw, there was a flip, and it does not always have to flip. Okay. So if you look at this, this is the snapshot. And then the question is, which of these options here to here is the appropriate representation of the history graph for that dot on this snapshot? Where are we going to place it? The dot is here already on the line. So it has nothing, look at it. It has nothing yet on this shape. Okay, so it's on the line, so we didn't have to flip the shape. All right, so let's see. So the answer is A. The shape remained. The dot is not on the shape, so we didn't have to flip anything. Then that's the major reason in why we didn't have to flip. So you can read also, check more details as to why it was not reversed, as what you've seen in the construction example. All right, so that is that about representing wave graphically using snapshots and history graph. So we'll progress to the mathematical description of sinusoidal wave. Okay, we've seen the word sinusoidal before, and we said that it's simply the description of wave motion as a function of cosine and sine. All right, so we'll say sinusoidal when we can describe it with cosine or sine. All right, so how do we mathematically represent wave? We want to see how shortly. So waves can come in many different shapes. That's why we saw the last one looking like a bent triangle, and then these ones looking like a spring, coiling spring. And it can come in several shapes. We have different shapes, but we choose to describe it mathematically with the focus on the sinusoidal wave. So no matter the shape it comes, we are going to use or assume that it can be described using the sine and cosine function. Okay, so and whenever we say sinusoidal wave, we're referring to actually when we looked at the last simple harmonic motion, we use the word sinusoidal to represent simple harmonic motion. So it means that this is a type of wave that is produced from oscillation with simple harmonic motion. So we can use sinusoidal relationship to describe it. Okay. So having established that, it means we'll be using either cosine or sine to mathematically express what the wave motion is like. So to do that, let's quickly understand the different structure of the wave. We know that the sinusoidal shape is in this coily form, the graph. So the wavelength is the distance between two successive crests. This is not new, or two successive troughs. And the speed is in the direction of the wave motion. Okay, so the wave moving to the right, we use this expression. So the shape here does not change. Okay, so we can see the map, the graph of displacement to with respect to position. We've already seen or know what this distance is, which is the maximum displacement we call the amplitude. Okay. So because we have seen that also when we're describing or discussing wave, yeah, in simple harmonic motion majorly, it did not change, but we have little modification to it. So the displacement as a function of position for this kind of wave is given by, remember we said as a function of position, is given by cos, that is amplitude cos 2 pi s over lambda. Our lambda is the wavelength, okay? So, but the displacement as a function of time, and we have yt, is also given as, because time, there's period in the description of time, that's why we have t. So we have amplitude cos 2 pi t time over period, that's small t over capital T. Okay, so if we know that the displacement, position, and time, combining these two expression for displacement, we have the expression like this: displacement as a function of position and time equal to amplitude cos 2 pi, this for position and this for time. You notice here there's a minus. There's a minus when, for the signs for wave, when displacement of a traveling wave is moving to the right. When it's moving to the right, we think, normally the right is the positive direction, but for waves, it's not so. When it's moving to the right, it's negative, and when it is moving to the left, it's positive. That is why we have positive here and negative here. Okay, so now we see that the combination of the equation is the same, but for the sign telling us the direction is plus because the wave is traveling to the left. Left normally is supposed to be negative, but for wave, reverse is the case. When it's going to the right, it's negative. When it's going to the left, it's positive. Okay, so let's look at this history graph. When we say history graph, it means the graph that is telling us the whole history of the wave motion. Okay, so this is a typical sinusoidal graph, and then the period is the same time between successive crests. Remains the period, and because it has successive crests, we can see the motion of the point on this string is simple harmonic motion. Okay. So still continuation on the wave and the mathematical expression we have, for example, this crest is moving to the right, as the wave is traveling to the right. So at t equal to 0, there are different direction the wave is traveling. That's what the figure is showing us. That the wave moving to the right will always be in the plus s direction, but to have negative expression. Okay. So why the wave moving to the left will have minus left direction, but we use plus as its sign. So ought to remember that the signs are actually opposite to the travel direction. Okay. So, and that is what this diagram or blocks of diagram is trying to describe to us, that during a time interval of exactly one period, the crest has moved for this exactly one wavelength. Okay. So we see our crest as it moves, we can count the wavelength. So let's see an example. A boat is moving to the right at 5.0 meter per second with respect to the water. An ocean wave is moving to the left. So the ocean wave and the boat, they are moving in opposite direction. So the wave has 2 meters between the top of the crest and the bottom of the trough. Okay, so that's 2 meters. The period of the wave is 8.3 seconds. So they give us the period as well. And the wavelength is 110 meters. At one instant, the boat sits on the crest of the water. 20 seconds later, what is the vertical displacement of the boat? So we can actually determine the vertical displacement without having to sink the boat. Okay. So let's see the visual diagram representation. The boat is moving in the opposite direction to the wave, and other parameters as it has given here. And we are looking for our displacement final, which is the displacement. Okay, so to solve this problem, we have brought out the items supplied. So the boat is moving to the right. What will be the direction in our formula? We said right, opposite. So the sign we use to know which is negative. Okay, so the boat is moving to the right at 5 meters per second. At t, final being 20 seconds. Okay, so since we have the t final, the position, remember position equal to v change in t. All right, that is what we applied here. T final. So the product of that will give us the distance, which is 100 meters. All right. So substituting into our equation, remember the boat is moving to the right, or the wave is moving to the left. Okay, so we have to apply this, moving to the left. We know the parameters given. So since we have our t to be 20 seconds and then the distance final being 100, we quickly substitute that into the formula given. For 100 meters and 20 seconds, we'll have A, which is given in the question as the amplitude, cos this plus 20 seconds to give us minus 0.42 meters. The question says, what is the vertical displacement? Okay, so the vertical displacement is simply minus 0.42 meters. Okay, So look at the fundamental relationship for sinusoidal waves. This is practically it. Velocity equals to distance over time. And because we're expressing this in terms of waves, so distance, we talk about wavelength, and then time talks about the period. And we know that 1/t is also Hz. So if we substitute that into this equation, we have V equal to lambda F. So this is the relationship between velocity, wavelength, and frequency for sinusoidal wave. Okay. So we should just take note of this, the reason being that we use this for calculation. An example, room temperature, at room temperature in air, the velocity of sound is given as 343 meter per second. Okay. So we'll look at another example. A sinusoidal wave with an amplitude, the amplitude is given, and the frequency of 100 Hz traveled with this speed 200 meter per second in the positive X direction. The positive X direction, that means it's going to the right. Write the equation of the wave displacement as it travels. Remember, the equation will have two, one for the right movement and one for the left direction movement as well. So we'll have first from the basic relationship, 2/100 gave us 2 meters. So the wavelength, we have an idea. The wavelength is having the wavelength is distance between two crests, 2 meters. So we want to construct the equation. We have the wavelength, then the period can be calculated from the frequency. If we do that, we'll have this value. So with this value in our hand, we can actually substitute into the equation we have, which is this very equation here. Amplitude cos. Okay, so take note of that equation. All right. The amplitude is given in the question as amplitude. Cos, we put that value there, we have what is supplied in the question. So we can either solve for t or solve for x. But this here is the expression for that wave that we describe now. Okay, so the next class activity, the three waves travels to the right with the same speed. Which wave has the highest frequency? All these two graphs have the same horizontal scale. All right. Remember what the question is saying, and I expect you to think it through. Which wave has the highest frequency? If you ask me, and we'll have the reason for the answer here. So let's progress quickly to the last part of the class, which is sound and light wave. All right. Every day we interact with sound, we interact with light. So we want to just take a peep into the details of how they are waves and how they actually come out to us. So let's begin with the sound wave. We saw an example of the sound wave before, where we described that the sound coming from the speaker acts on the air around it, bring about compression, and then as it travels away from the speaker, this continues to happen. Compression of air takes the sound to the destination. Okay, so we'll have the area of clustered air particles to be the compression, Then the rarefaction, the area of sparsely air particles. Mm. So this continues to go in the direction until it gets to the human ears. Okay, so we'll have two major characteristics: the compression, which is this region, and then the rarefaction, which is the region when there is nothing or very little. So graphically, we can see that compression is when the trough is up, no, the crest is up and trough is down. This is rarefaction and this is compression, rarefaction, compression. So the sound wave is a pressure wave. It compresses the compression at the crest, like we said earlier, and the yeah, the trough depicts the rarefaction. So we have also explained this before, but we did not use the word rarefaction. So this is just the only new addition we have. And also to emphasize that the human normal hearing is within the range of 20 to 20 kilohertz. Anything below is regarded as low pitch, or high pitch is the ones that are higher. Okay, so take note of that range of the human hearing. Let's take an example. What are the wavelengths of sound waves at the limit of the human hearing? So the limit, which is limited to 20 hertz to 20 kilohertz. That's the range. So if this question did not specify the values and saying the range, we have to use the the figures within that range. All right. So to solve this, we have that for the three wavelengths, the fundamental relationship for wave frequency and time is what we have: V equal to lambda F. Okay, so if we solve for the least using this relationship, remember we said this at room temperature previously. It's not given in the question, but if we're asked to solve such, we will supply the constant as well. Then we're solving for when the sound is at the low side, which is 20 hertz for the human ears. So I've measured 17. We try it again for 500 hertz. Okay. Doing again also for the 2000 kilohertz, we have this value as well. We just substitute, use the speed of light as our velocity. Okay. So that's pretty straightforward there using this relationship. Now, this is the range of the hearing for different animals. You see where the human being falls in, 20 to 2000 and 20,000 hertz. Okay, so these are other animals and their hearing range as well. So we'll take this example, almost at the end of the class. So to make a sufficient detailed ultrasound image of a fetus in its mother's uterus, a physician has decided that a wavelength of 0.5 millimeters is needed. What is the required frequency? So once wavelength is given, the frequency can actually be determined. We first of all write the relationship here. Okay, the relationship equation can just keep rotating it. Can make anyone the subject of formula at any time, depending on what is applicable. Okay, so we're asked to look for the frequency. Um, the velocity is given the ultrasound. Okay, this is the wavelength as given here, converting it to meters. And then we have the velocity. Great. It is ultrasound image. So by the time we divide this with this, we now have 3.1 times 10 raised to the power 6 hertz, which is 3.1 megahertz. Okay. That is what the physician used on the determination of or examination of the fetus in the womb. All right, so the very last topic for this class is the light and other electromagnetic waves. Now, the interesting thing about this is that we already know a lot about how electromagnetic waves behave, but we just want to point out the certain facts, one of which is that a light wave is an electromagnetic wave. We already know that. And all electromagnetic waves travel with the same speed in space. So we have the speed of light in space or in vacuum is given as 3.0 times 10 raised to the power 8 meters per second, right? And also we want to emphasize that all other all the electromagnetic waves such as this wave all will have the same physical characteristics as that of light waves. The only difference is that we cannot actually see them with our bare eyes. Okay, so this is a typical electromagnetic spectrum ranging from, this is how the frequency is going, ascending, and then as frequency increase, wavelength decrease. Okay, so we'll have the frequency of the AM down to that of X-ray and the area for visible light going from red to purple. Okay, so take an example. The wavelength of a microwave in a microwave oven is 12 cm. What is the frequency of the wavelength? Use this relationship. Asking you for frequency when they did not give you the period or time, or calculate it or say it in the question in terms of the description of position. When you're given such problems, we cannot just use the inverse of period because we have an unknown as well. So we always use this relationship, F equal to V over lambda. So we use the value for the speed of light here because we said the microwave, okay? Which normally when you're using it, you turn microwave off to, so we're actually using the speed of light as a 0.3 above or electromagnetic wave behave the same way and they have the same speed. So we have that the frequency is actually 2.5 gigahertz. Okay, so we'll have some practice question for you here. I want to encourage us to go through it, read the comments, and also do the assignment and submit as when due. Okay. Thank you so much. I'll be uploading the correct slide and recording for the last lecture. All right. Have a great day. Bye-bye.